Hello, dynamics people. Um, this video, excuse me, will discuss chapter 17, sections 2 and 3 of Hibbler. These are really important sections, especially 17.2. This section describes the basic equations which relate moments and angular acceleration, as well as forces and translational motion. So pay close attention, read through these sections very carefully. The goal for today will be able to write down 3 equations of motion for a rigid body undergoing planar motion, and then we will actually solve these equations for translational motion. We'll save rotational motion problems for next time. So today we're going to write down problems where they could rotate, but we won't quite let them rotate. You might wonder, well, what good is that? So anyway, so I will explain later what good they might be when we do our examples. So usual outline of the activities. You want to be able to draw free body diagrams, want to write down equations of motion, and understand where they come from. We'll have a reading quiz, and then when we meet in person, we'll go through the concept quiz and go through group problem solving. Here's our reading quiz for the day. When a rigid body undergoes translational motion due to external forces and translational equations of motion, the translational equations of motion can be expressed for center of rotation, center of mass, arbitrary point, all the above. The best answer is B. The equations of motions naturally describe the motion of the center of mass. The rotational equation of motion about the center of mass of a rigid body indicates that the sum of moments due to the external loads equals A, I alpha, B, MA, C is a combination, or D? Well, if you've done the reading, you'll know the answer is A, and I hope to explain why that is today. Here's a typical kind of problem that we have in mind. And I know you might be thinking that is Thomas's high school drive your tractor to school day, but we're supposed to not focus on the tractor and instead focus on the boat. So a typical kind of problem might be, what acceleration will cause the boat to start to tip, or what are the different normal forces underneath each wheel? And both of those are problems that, although they don't have any rotation in it yet, you're sort of studying the threshold for possible rotations. And so understanding the role of torque and moments are going to be important. Here's another kind of problem that we will have today. We have a truck or a forklift lifting a box. It's undergoing, you might think it's just undergoing general motion, but it's really not, because you notice the fork doesn't rotate. So the box undergoes curvilinear translations, but not general planar motion. Sort of an interesting question. If the load is raised too quickly, will the crate slide to the left or to the right? Think about that. Okay, so the planar equations of motion. I'm going to switch screens here and then work through these so you can really understand where it comes from. All right. So in this situation, we're going to imagine that we have a body. Oh, before we get started, I wanted to remind you of vector identity. Remember, A cross the quantity B cross C equals ABC equals back cab B times A dot C minus C A dot B. Okay, that's an identity we've seen a few times. If you can remember that, it makes the derivation of this of the equations of motion a little bit simpler. So what we're going to imagine is we have some sort of an object, and we're going to imagine we have an axis of rotation passing through some point P. And the axis of rotation, if you want, if this is a planar motion, we can let point P, the axis of rotation through point P, go into your eye. Okay, and so we can imagine this thing's going to rotate like that. So, not surprising, the general translational equations of motion simply say that F net equals mass times acceleration. But you might say, well, we've been talking about, there are lots of little points here and there, and we've talked about acceleration of one point relative to another, blah, 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 blah. What point has this acceleration? And the answer is, it's the center of mass, G. So we'll put the center of mass here. Okay, the center of gravity or center of mass. So these give us, for planar motion, these give us our two translational equations of motion. I won't worry about those too much. This is exactly what we did in Physics 1. Let's go in and really pull apart what happens on the inside of this distribution of mass. And we're going to really focus on rotational motion. So let me kind of redraw my blobular sort of shape. And imagine I have a point P here. And then let's focus on a little piece of mass here. It's going to be a little piece of mass. We're going to say it has mass mi. Eventually it'll become differential in size. Now, there are, up here we were talking about the total object, the overall motion. Right now I want you to focus on this little piece. So what are the forces that could act on this? What forces could act on this? Well, the forces on this little mass could come in two basic types. You could have external forces. I'll write those with capital letters. And you could also have internal forces. I'll write those with lowercase letters. So internal forces might be forces coming from maybe the neighboring little blobs of mass pushing on mass I. So the net force on the ith piece of mass is going to be the sum of the external forces. External forces could be coming from the outside plus the internal forces, right? And using Newton's second law, for this little mass, that must equal the ith mass times the acceleration of the ith mass. Okay, so hopefully that's not too controversial. Now, I said we're not really going to focus on the acceleration, the translational motion. We already know where those equations are what they're going to shake out to be. What we're going to do is focus on the rotation, or well, we're going to focus on the rotation of point I about the axis of rotation, point P. So to get at this, we're going to focus on the following quantity. R I relative to P cross F net I. That's the net moment on mass I. Okay. Oh dear. I got my arrow in the wrong spot. Right? The torque, or the net moment on this little bit of mass. Okay. That's fine. Now we're going to use our formula coming from Newton's second law to say this is mi times ai. So I get that the moment on the ith mass is equal to r I relative to p cross mi ai. And then what we're going to do is use our formula for relative acceleration. We know that ai, let me put it over here in parentheses, but ai equals ap plus alpha cross r ip minus omega squared r ip, using our relative acceleration formula that we learned about last time. So if I substitute this into here and take the cross product, I get the following. It's going to be RIP cross AP plus RIP cross alpha cross RIP minus omega squared, and then I get RIP cross RIP. But that's a big fat zero because the cross product of a vector with itself is zero. This factor I can reduce using the triple vector product identity to write this as alpha times RIP squared minus RIP times alpha dot RIP. And for planar motion, this equals 0. If we were in 3D, you'd have to keep this piece. So we're left with only this term, which simplifies a little bit, or which is a little bit nicer. So let me kind of summarize that. So when I have a blob and I have a point P with an axis of rotation running through point P, and I focus on a little bit of mass I, that the net, oh dear, the net moment about point P, sorry, the net moment of I about point P is R I relative to P cross the acceleration P plus alpha cross, oh, there's a cross product there. It's alpha vector times RIP, and it would be the magnitude squared if I was writing this as vector quantities. Or since we know it's a vector quantity, when you say something squared, you just know that it means the dot product with itself. Now think about this. The torque or moment will point in the z direction, alpha points in the z direction, and if you're careful and you think about it, sure enough, the acceleration is in the plane, the radius is in the plane, so this cross product will be in the z direction as well. So these are all in the z direction, so that's good. That means that these are okay. And I forgot my factor of mass. So when we look back here, there's a factor of mass right there, and I forgot it. So everything, so this would be, there you go. That was my cheat. I didn't find the moment, I found the moment divided by mass. But let's reinstate the mass here. So I'm gonna have a mass here, and I'll have multiplied this one by the mass. Okay, now, if we were to add this quantity over the entire body, what would happen is the moments coming from the internal forces are going to just cancel out because of Newton's third law. And you're only going to be left with the moments from the external forces. So we can find only the external moments about point P and, well, I would have to, what's going to happen? Well, I'm going to add up all these little chunks. I'm going to associate, I'm going to go from mi to a differential dm, and then this is going to become the integral dm. And the first term is going to give me ri vector. And notice this acceleration was the acceleration of point P, not, had nothing to do with the label I. So actually, get rid of the I. Actually, this is the relative vector to some point from P, but because this acceleration vector is constant, it pulls outside the integral. This number would be the same everywhere through the body. This vector, sorry, would be the same everywhere through the body. So it pulls out of the integral. Plus, alpha is a constant throughout the body. So that pulls out. dm. Well, that looks interesting. This is nothing other than the moment of inertia about point P. Now, what could this be? An integral of position over where you're integrating over masses. But this is nothing other than the mass, total mass, times, well, this would be nothing other than the center of mass position. Cross AP. And that is our first formula. We have to add these. Okay. So this says that the sum of torques about a point P are given by the mass times R cross A, where R is measured from the center of mass to point P. Sorry, is measured from P to the center of mass. It's the position of the center of mass relative to point P. Maybe I should put relative to P. Well, okay, just leave it. Cross the acceleration of P plus I times alpha, IP times alpha. And that's our first equation that we might want to know. Now, special case. If P equals the center of mass, or center of gravity, then that would mean that the relative vector from P to the center of gravity would equal 0. I suppose I should put a P there just to be really clear. This is from P to the center of mass. Then this would be 0, in which case we arrive at our first important result. For rotations, about the center of mass, or center of gravity, then the sum of all the external moments equals the moment of inertia about the center of gravity times alpha. Okay, that's a really useful formula. In fact, we would use that most of the time, I think, but not always. All right. Now let's go back to our previous formula. Previously, we kind of had the more general formula, which I wrote over here, so I'll rewrite it, which said that the sum of the moments about point P equaled R center of mass relative to P cross acceleration Okay, so that was our more general equation. And even if point P isn't the center of mass or center of gravity, we could express things in terms of what does exist at the center of gravity. So I could say, for example, that AP equals AG plus R PG cross I'm sorry, these backwards again. This would be plus alpha cross R PG minus omega squared times RPG. Remember, RPG would be minus RGP, which I was calling RCMP, so the vector to the center of mass. Okay, and taking this and plugging in here, taking the cross product again, I get the following. I'll leave that as an exercise. You can take this, plug it into here, and you're going to get the, using the triple cross product, you're going to get the following here. You're going to get the R G cross P, or P cross AP equals R Okay, so after doing the triple cross product again, one of the terms goes to zero always, even in 3D, and one of them goes to zero just because of 2D properties. So this would be the center mass position relative to P, center mass position relative to P. And then I end up with the cross product of with respect to the acceleration of the center of mass, and this is alpha times the relative position between point P and the center of gravity squared. And the other little nifty thing is using the parallel, or not nifty, but the other little property that we have is using the parallel axis theorem, that the moment of inertia about point P is the moment of inertia around the center of gravity plus the relative position squared times the mass. So when I plug in these two facts into my formula for the moment about point P, that equals R G P cross M A of the center of gravity minus, again coming from this term, alpha times the mass times R center of mass squared. And then if you go back, so this term is what I just wrote down. I also have to add in this term, so IP times alpha. So that's going to be plus IP times alpha. Well, that's going to be IG times alpha plus this term. And you'll notice this term and this term cancel. So when I have a point that isn't the center of gravity, I get the following formula. All right, so what does that mean? So what you see is, so this is my other form. This is about for a general point P, and I can express it in terms of quantities related to the center of gravity, which is convenient because the center of gravity is the point that we have equations of motions for. This appears in the translational equation of motion. And furthermore, in terms of computing moments of inertia, usually the center of gravity is the number that we actually know. So that's kind of nice. This factor and this term are related to the center of gravity, and this is the point that kind of knows that you might not be summing moments about the center of gravity, but instead some other point P. So these two are called kinetic moments sometimes. Sorry about that. I guess both of these are kinetic moments. So one of the ways that sometimes people might think about these is that you have these kind of dynamically determined moments coming from forces, and the rotational equation says that the dynamical forces or moments must equal the kinetic moments. What do these terms mean? Let's see if I can give you an idea from a picture. So let's imagine that we have an object. Okay, so let's imagine I'm going to assert that alpha equals 0. Okay, so how could that be? So I have a point here, and let's say we exert some force on this shape. Let's say we exert some forces here, something like that. So the shape is going to have no rotation, so it undergoes some sort of translational motion. So later on, oh, sorry about that. Everything's moved over to this, to look like this. So here's the thing, you could say, oh, okay, well, wait a minute. How is it possible to have alpha equal to 0? Because, it looks like when you sum the moments about, say, this point A, then maybe it looks like you get the sum of moments about point A. Well, it looks like you should get not 0. So why didn't it why didn't you have why is alpha possibly 0? And what happens is that what happens is all of the moments that you use actually get used just to translate A, in some way of thinking of it. So the way I kind of like it, so what we really have is MA equals R RG relative to A cross the acceleration of A, sorry, of the center mass, G times M plus IG times alpha. We're saying that one's 0. So why is that? Well, what's happening is the moments are are, how do I say this? Here's how I would say it. If the center of gravity weren't moving and you were to follow A forward in time, indeed, it would look like a rotation. The object would kind of look more flat, let's say, or more, maybe more vertical. It would look like a rotation. But some of the moments about A are what you need not just to have a rotation, but in fact, just to carry the center of mass along with point A. So if you didn't have this term, that's what you would get if you said that the center of mass was fixed and A kind of passed it by. And indeed, that would correspond to a rotation. But really, because in this situation, because I said that alpha was 0, what's happening is this moment about A is exactly what you need to kind of bring the center of mass along with point A as it moves. So I don't know. Sounded better in my head when I tried to explain it, but that's kind of how I picture this term. All right. So let's go back and kind of box that in, to show these boxed in equations. So I've got two boxed in equations here for rotational problems. This is the equation you have about an arbitrary point, and this is the equation you have about the center of gravity. Obviously, this one is simpler, but sometimes you don't get to work with the simpler version of things. Okay, now let's jump back into our slides. Okay, so it's going to be similar, just maybe not quite as expanded. They're doing the same sort of thing we were talking about, R cross F. Internal forces are going to cancel, so you only get external forces. And you get the center of gravity position cross mass times acceleration center of gravity plus the moment of inertia about the center of gravity times alpha. Notice they hide a whole bunch in the phrase can be written as. All right, and the can be written as is the algebra I just did on the previous slides. So these form our equations down here at the bottom. So we have F equals ma, where the acceleration is the acceleration of the center of gravity. Those are the first two translational equations. And then we have our rotational equation. Either you can apply it about the center of gravity, or if you need to specify it about some other point, you have to use this form where you're summing over, you're saying basically the dynamical moments is equal to the sum of the kinetic moments. Okay. If we simplify our life for the situation where alpha is 0, then that reduces one of our equations down to 0, or at least it makes it simpler and smaller. Okay. Now, there's one other little caveat. Well, not caveat. The equations I wrote down, when you work with problems that are nice and Cartesian, then you want to use rectilinear coordinates. If you are doing general kind of curvilinear translations, then you want to work in tangent and normal frame components. And the general formula I gave you is right for all coordinate systems. It's just that if you write it out, here's some path, and they specify something called E. That's a displacement from the center of mass along the normal direction, and then they specify a quantity called H, which is a displacement from the center of mass along the tangent direction. Then that cross product between the center of mass position and the acceleration takes the following form. Personally, I don't ever remember this. I just kind of have to think about it and figure it out on a case by case problem or case by case situation. So what's a general process? Well, okay, you have to choose coordinates. So basically, is it Cartesian or is it not? Should you use rectilinear coordinates or curvilinear coordinates? And you want to draw a free body diagram, get every external force, and then you want to start counting knowns and unknowns, and you have your various equations of motion. So translational and rotational equations of motion. All right, here's our first example. So we have this situation where there's a cart being pushed, and we're told that the total mass of cart and packages is 100 kilograms, and we're told that there is a total force of 100 newtons applied. And the problem has you find the they want you to find the normal force each wheel. And the problem, they also find the acceleration, so we'll do that too. All right, so let's go through this. So we have the following situation. We have the shopping cart. And we are told, so we have these wheels here, and they call these B and A. And then we have a force being exerted downwards, and that follows a 3, 4, 5 right triangle. This is 100 newtons in magnitude. The center of gravity is over here, and we're told various lengths. We're told that this distance is 1.2 meters. We are told that this distance is 0.3 meters. We are told this distance is 0.4 meters, obviously not to scale, and we're told that this distance is 0.6 meters. Finally, we're also told that this distance is 0.5 meters. So just check that, 1.2, 0.3, 0.4, 0.6, 0.5. And you'll notice that means that between G and the top of the handlebar up here is 0.7 meters, as well as this being 0.7 meters. And that gives, there's a little simplification there. Okay. Ooh, sorry. All right. So let's go through this. So the force, all right, so then my equations are F net in the x direction. Well, what are the net forces in the x direction? We're going to ignore any friction. And in that case, I really, in the x direction, I just have 100 times, well, I have to figure that, 100 newtons times 4/5 in the x direction. And that should equal the mass times acceleration in the x direction. So that's going to be, for the mass was 100 kilograms. So this will be AX is 0.8 meters per second squared. Okay, so there's that. Mass for that wasn't too hard to find. Let's write down our net force in the y direction. So in the y direction, I have the vertical component of that downward force. So I'd have minus 100 times 3/5. And then I'd have a weight going down. And then I would have two normal forces acting up. Right? And using the fact that the cart has a mass of 100 kilograms, I learned that the normal force A plus the normal force B equals 1041 newtons. Or I can turn that around and say normal force of A equals 1041 minus the normal force of B. Just solving this equation. All right. So let's count knowns and unknowns here. So we've used the x equation, and that gives us an acceleration. We've used the y equation, and that gives us a relationship between the forces on wheel A and wheel B, but we don't know either separately yet. That's why we're going to need our torque equation. For this problem, I'm going to look at moments about g. Okay, so if I go back here, a couple ways you can do it. You could either write this out very formally and find the moment of the hands pressing down on the cart, or what you could do is look at this and say, okay, the downward component of this force makes it want to rotate in a positive direction, and it would be the downward component times the perpendicular direct distance, which would be 0.7. And then you could also say that the forward component, that would make it want to rotate in a clockwise rotation, so to be a positive torque, and you could write that down as the positive component of the applied force times the perpendicular distance for it, which would again be 0.7. I think that's going to be easier rather than kind of formally writing out the cross product of these vectors. So the moment caused by the push is going to be, see, the positive torque or positive moment is going to come from the downward part. So that's going to be 100 times 3/5 times the perpendicular distance, which is 0.7 meters. Well, the whole thing would come out with Newton meters. And then there was a clockwise rotation, so a negative rotation coming from the horizontal component, and that will be 100 times 4/5 times, and that had a 0.7 as a kind of lever arm there too. And ultimately you get 1/5 times 0.7. So that would be 20 times 0.7. That would be 14. Okay, so this is the moment coming from the push. The downward component gave a positive torque, and that came with a factor of 3/5. The forward push gave a negative torque, so that came with a 4/5. And then now I have to add in the moments from the wheels. All right, so the total moment, remember it's not rotating, so the total moment so alpha is 0. That's going to be 14. Oh, should have been more careful. This is negative 14 because the forward torque is stronger than the downward. The torque from the forward force is bigger than the torque from the downward force. Minus 14, and then I have to add in the moments from the two wheels. So now I look at this, and I see that wheel B pushes up, and that makes it want to rotate in a clockwise rotation, so that'll be a negative. And that was going to be the normal force at B, and perpendicular distance is going to be 0.4. Plus 0.6. Okay, so this is my equation coming from the moments. Or if I rewrite this, I can say that 14 equals in A times 0.6 minus in B times 0.4. Look, going back to my previous equation, I had that in A was 1041 minus in B. So I substitute that into here, and this gives me 0.6 times 1041 minus 0.6 plus 0.4 times NB is just NB. And solve for NB. And we find 610.6 newtons, and back substitute and get NA equals to 430.4 newtons. Whew. And that's how that goes. So let's kind of recap what we did. We wrote down our three equations of motion, three equations of motion. In the x direction, we use that to find an acceleration. In the y direction, we had the y components of the pushing force, the weight, and the two normal forces. Those two didn't give us enough information to solve for the normal forces. We needed our torque equation, our moment equation. And we summed the moments about the center of gravity. I meant to highlight that one of the nice things about using the center of gravity is that you don't ever have to worry about including a torque due to a weight. So that's kind of nice. Okay, let's see how we fared. Good. Same acceleration. And good and good. So they agree with us, as they should. Their basic method is the same, I believe. All right, let's do another example. Here's a situation where you have a truck which is accelerating, and you have this, they call it a table, but it's just some object, and they tell you the coordinates of its center of gravity, which is really all you need. And they tell you that it's standing on two legs. If you can kind of see this, there are legs here, and here. Okay, so the object is standing on two legs, and if the truck goes too fast, the object is going to start to move. It's not safe. So the task is given a coefficient of static friction of 0.2. There is a the table has a total mass of 100 kilograms, and they give us the coordinates. Find the maximum acceleration which is possible without causing the table to move relative to the truck, and find the corresponding normal reactions on legs A and B. All right, so we're going to need a diagram, we're going to need to label everything, and then we're going to try to think this through. Now, but we're after the maximum acceleration and then the normal forces. Oh, come on. There we go. Trying to insert a new slide. Okay, so what we need to do is to slide here. First thing I need to do is get my PowerPoint back up. Sorry, that's there we are. Not sure what happened there. Okay, so I have my truck, and I have these 2 points A and B. And I have the geometry of it. We want to find the maximum acceleration before the table starts to move, as well as the normal forces at points A and points B. Now, I will tell you the book kind of jumps the gun here. There are actually two ways that you could think that this might start to move. It might be that the first sort of motion is a sliding motion along the bed of the truck. The other option is that the object starts to want to rotate even with no sliding. You know, it could be that the normal force at point A gets to 0 and then it wants to rotate. And so really, we should solve both problems. One, where the object just wants to start to slide, and the other when it just wants to start to rotate, and see which of those gives you the tightest constraint on the acceleration. Now, looking at it, seeing that the object is kind of has a sort of a lower profile, it's wider than it is tall, well, or about the same. I guess it's the same height as it is wide. I expect then the most stringent constraint to come from a lack of slipping. But let's go through, just because it's illustrative of what you might have to do in other problems. Okay. So here we're going to work out the constraint imposed by no slipping. Let's keep the colors there. So here we want we want no slipping. Which means that right when you're going as fast as possible, that means that the frictional force, which is static friction, is going to equal mu s times the normal force. And if I kind of think about my shape here, have this sort of kind of irregular shape thing here, and there's a leg right here at point B, and there's a leg right here at point A, and the center of gravity's right here, and I'm told that this distance is 0.75, and I'm told that this distance is 0.6, and I'm told that this distance is 0.9 meters. Everything's in meters. And this is the center of gravity, G. All right. Well, let's go through. We're assuming no slipping first. So this is, we're going to write down our equation. So we'd say that F net in the x direction is going to be, well, what are the forces acting in the x direction? If I draw my shape here, I have a friction force at A, or sorry, this is B, and I have a friction force at A, and those are really the only horizontal forces. So I would say that this is mu s times the normal force at A plus normal force at B. And that must equal the mass times the acceleration. Okay. Now, what other forces do we have at play here? Well, we have normal forces at A, the normal force at B, and then there's a weight acting straight down. So I add up forces in the y direction. I'm going to have normal force in A plus normal force at B minus the weight. And we immediately see then that the normal force of A plus the normal force of B equals mg. And then from that, I immediately see that A max with no slipping, the no slipping condition, gives me A max equals mu s times g. I plug in numbers, and that gives me 1.962 because mu s, sorry, meters per second squared, because mu s is 0.2. Now let's find, we still need to find the normal forces. So to find the normal forces, I've used my y equation to say that normal force A plus normal force at B equals mg. I need to use the torque equation now to figure out the way that the force is distributed between points A and points B. So to do that, I'm going to sum the moments about G. And because I know alpha is 0, that means that the sum of the moments about G should be 0. And I just look at the picture and do that. So when I look at the picture, I see that the friction forces are all generating counterclockwise positive torques. I see that the normal force from A generates a negative torque, and the normal force from B generates a positive torque. And the various geometric quantities are specified up there. So from the friction forces, I get each one has a lever arm of 0.75 meters times the friction force. And then I also had a positive torque coming from point, this should have been an A. From point A, oh dear. I have my A's and B's backwards in this picture. I apologize. A is in the front, B is in the back. A should be a positive torque, B should be a negative torque. And that would be 0.9 times the normal force of A minus 0.6 times the normal force of B. Because B in the back has a perpendicular distance of 0.6, and A in the front has a perpendicular distance of 0.9 meters. So A gets the 0.9 and B gets the 0.6. And those have to add up to 0. But I know that the frictional force has to equal the mass times acceleration. A times mg. So I'm just going to write these out. I get the following equations. I get NA plus NB is mg. And then I have the following. I get mu k mg times 0.75 equals 0.6 in B minus 0.9 in A. So I take this equation and this equation, two equations, two unknowns, and I solve for NA, and I get 294.3, and I get solve for NB, and I get 686.7. And these are newtons. Okay, so let's just check. Well, okay, so that's what I get, assuming that the first way that this thing could start to move is to slip, and that will prove to be the correct assumption. Other option, which the slides or the book doesn't entertain, but which logically was a possibility, was that before it started to slip, it actually tried to tip. So we could also solve for a no tipping condition. All right, and let's see how that would work. So in this condition, this weird shape, point G, B's in the back, A's in the front, the acceleration is to the right. In this condition, well, okay, let's write down our equations. We still have that the force of friction from A plus the force of friction from B is equal to the mass times acceleration. But if we aren't imposing a no slip, like an impending slipping condition, then I can't use mu sub s. I just don't know anything about these. What I do know is that the normal force from A plus the normal force from B must still equal the weight. That's from the y equation. This is from the x equation. This is from the y equation. And then if I want the no slipping condition to hold, I still would say that the total moment about point G is 0. Sorry, no, that means it's not going to tip. It hasn't quite tipped, but it's almost going to. So what I also want to require is that if it's almost ready to tip, it's almost ready to pop up and flip out of the back of the truck, then the normal force at A should equal 0. Which, if you think about it, also is going to mean that the frictional force at A is 0. So Okay, so the frictional forces have to be 0 if we're almost ready to tip. Okay, so let me go ahead and impose that constraint. All right, so that's what I have so far. But I still don't know the frictional force at B because there's no correct connection between the normal force at B and the friction force at B unless slipping is impending. So to proceed now, what I need to do is work out the moment about G produced just by the forces at point B, which would be the friction force and the normal force. So what are those forces going to look like? Well, the normal force goes up, and the friction force at B is going to the right. The normal force is going to make a negative torque, and the friction force is going to make a positive torque. So that's going to be minus 0.6 in B plus the friction force at B, which I don't know, but it's there. It's 0.75. It has to equal 0. Turning that around, then I get that, let's see. I would get that using the fact that the friction force equals MA, I would get 0.6 in B equals FB times 0.75, and I'm going to plug in these two results and get 0.6 times mg equals 0.75 times ma. So A would equal so the max acceleration with no tipping condition imposed would be 0.6 over 0.75 times g, and if you plug in numbers, that's 7.85 meters per second squared. So we get two possible accelerations. If you assume that it doesn't tip, you get 7.85 as the max acceleration. If you look at the constraint imposed by no slipping, you get 1.96 as the max acceleration. And we're looking at the most constraining of the two. And so this is going to be the actual answer. Let's see how we fared. So comparing to what they have, sure enough, that's what we get. And those were the two normal forces that we found. In the slides, they didn't even consider the possibility of tipping, but in some examples, you have to consider that. Okay, so I will start class with, so here's a situation. We have a 2-pound disc over here attached to a uniform 6-pound rod and a frictionless collar, and that we assume the disc rolls without slipping. What is the correct free body diagram? Take a look at those. I'll ask you about it when I see you next. And similarly, now we have, it does slip, so we have kinetic friction, same thing, which is the correct free body diagram. All right, see you guys next time.